In the previous lecture, we talked about gradient descent. First, we talked about cost function or loss function, and then we talk about gradient descent algorithm to solve to find the minimizer of the cost function, to find the weights and biases that minimize the cost function, right? So we have not discussed about possible problems with those algorithms. Actually, indeed, gradient descent algorithm has its own issues. Has many issues indeed. This is today in this lecture we talk about one of the many issues, which is a local minimum problem. Let's illustrate the local minimum problem using an example. Okay, this is an example. We have this neural network, X1 and X2, two input and one output. There are three parameters, W1, W2, and P1. Okay. In this case, let W2 be equals to 1. And I believe we let also P1 be equals to 0. You can see the output is sigmoid of W1 times X1 plus W2 plus X2 plus 0 plus P1 equals 0. Okay. Then we do the sigmoid function, right? And this is a cost function. And let's suppose these are the data, X1, X2. These are the data points, okay? We have black dots and red squares. Black dots belong to one class and red squares belong to the other class, okay? Y equals 0 or 1, okay? Now, if we let, okay, W2 is always equals to 1, okay? If we let W1 equals to 0, then we will have this decision boundary. Okay, this decision boundary, right? And with this decision boundary, we make total of 5 errors. Okay, the three red squares on the left top corner is being classified wrong, and the two black circles is being classified wrongly. If we let W1 to be 1, okay, good. So we turn the decision boundary. So the three red squares which were previously classified wrongly, now they are being classified correctly. And the two black circle that which was previously classified wrongly is still wrong. Okay, so we go from 5 errors to 2 errors. Okay. If we let W1 equals to -1, we end up with 3 errors, which is better than 5 errors. But between W1 equals to -1 and W1 equals to 1, we go from 3 errors to 5 errors to 2 errors, right? W1 equals to -1, you get 3 errors. W1 equals to 0, get 5 errors. W1 equals to 1, 2 errors. Okay, so there's increase of errors as you increase W1 from -1 to 1. W1 equals to 1 is something like this, what you want to achieve. Okay, if I set W1 to be very negative numbers, I make lots of errors. Of course, I set W1 to extreme values, I make lots of errors. Okay, so if I plot the cost as function of W1, I see this plot. Okay, this is the actual plot that is computed. The actual loss is computed. I wrote a code to calculate. cost exactly, right? It's cost exactly. Because I know exactly where the data points in error code to this. You can see that there's a little bump at W equals 0 where we have 5 errors, right? And there are two basins. Okay, the basin on the right is better because it's lower, cost lower. Basin on the left is good, but it's not as good, right? The cost is higher. We want to go to the basin on the right, basically, right? So if we do gradient descent, we, as said, we do not know what are the good set of weights, what is a good W1 from the start. So we make a random guess. Say we make the guess W1 equals to -5. Here, we end up here. We do gradient descent, 1 step, 2 steps, and 3 steps. Okay, we do any number of steps of gradient descent. We stop at 3 errors because this is a local minimum. This minimum, the lowest you can go if you start from W1 equals to -5. Okay. Let's say we get a little bit more lucky. We start W1 equals to 6. We do gradient descent step by steps, right? In the end, we end up here. So it depends on where you start. You get a different answer or different lowest cost possible cost. So this is called the local minimum problem, depending on where you start. Okay. So local minimum problem is everywhere actually. Please don't think that this is a synthetic example that I come up with, but it's everywhere in when you do optimization. Okay, for deep neural network. Okay, you can try the TensorFlow playground for the XOR example here. This TensorFlow playground. You can try it yourself. Okay, you make this network. Is in principle is able to differentiate these, classify all these dots correctly. Okay, but you try several times. Please try, let's say 10 times. You will see that among 10 times, 2 or 3 times, depending on how lucky or how unlucky you are, there will be a few times where you cannot optimize the network. Okay, you can get these local minimum issues. Okay. Okay, that's all for this lecture on local minimum. Thank you.